Hello friends, recently we have studied the potential energy and its equations and formulas, how to derive that equation, everything we have seen in last video. Now we will say the principle of minimum potential energy. So what with the word minimum is showing that there should be some minimum conditions that may be extremized conditions, it may be minimum or maximum. So the total potential energy, if the extremum condition is minimum, then we have to state this as a stable equation, and we can find the total potential energy. So we need to find first the deformation u by using the stress strain method. So if we want to find the total potential energy of body, to find out the deformation we need to consider the one displacement. Okay, so we can consider the bar which is having stressed bar which is having the fixed positions or fixed points on both the ends. So we can have the length of that bar is 2L. So for this problem we need to find the displacement, and we have to just consider u is equal to a0 plus a1x plus a2x square, as we have stated earlier, where a0, a1, a2 which are the constants. So to find out the u, first the method is called as the Rayleigh Ritz method. So we will follow the RR method, that is Rayleigh Ritz method. We can explain this method for considering the simple problem which is having a bar which is fixed at both ends, and point P load is acting having a magnitude P at the mid of that bar. So considering the boundary conditions at the x is equal to 0 to x is equal to 2L, and at point P it is x is equal to L. So we can assume the deformation due to local load is equal to u is equal to a0 plus a1x plus a2x square, because this is just the assumption what we are finding. So we can take it as equation number 1. So boundary condition for beam is at u at x is equal to 0 is equal to 0, and u at x is equal to 2L is also 0. So x is equal to 0 and u is equal to 0, we can put these conditions in the equation number 1, and we can get the a0 value, that is equal to 0. So now again we can put the second boundary condition, that is u at x is equal to 2L is equal to 0, and we will get the value of a1, that is equal to minus 2L a2, and this is called as equation 2, and put this equation in this value in equation number 1, and we will get the value of u in terms of x and L. So we have get x into a2 in bracket x minus 2L, and this is gave as equation number 3, and there are some steps you have to follow in Rayleigh Ritz method. So first one is assume a set of function, that is assume displacement field. So phi I, which is the function of x, y and z, which is in terms of u, v and w. So u is equal to summation of ai into phi x, y, z, and v is equal to summation of ai, aj and phi j. W is equal to summation of ak, phi k, and here we have the values of phi 1, phi 2 and phi 3 is equal to 1, x and x square respectively. Okay, so this shows that the u bar is becoming a field and ai is the parameter. So u bar should be kinematically admissible and the boundary condition should be at the u bar. So we are assuming u bar as a function pi, that is potential energy. So we can compute this pi, it is potential energy. As we know u, then we can get the elasticity, and we can get the sigma, and if we get both these three, then we can easily get the value of potential energy. So if we are considering as a minimum potential energy, so that the potential energy with respect to a1 is equal to 0. So we are solving for ai. So to get u bar, so to get that one, we know u bar, e bar and sigma bar we have to find, and then we will get the value of or approximate solution for the potential energy. So this is the problem we have over here. So for 1D problem we have assumed, okay, the conditions are applied as given over here. So this is just condition, we are taking a problem on that. So for minimum potential energy we have considered pi is equal to half of integration of sigma t e dv minus summation of ui t into pi, because all the other terms, that is traction force and point load, this is what we can say, the body force and traction force are not given over here, we are just taking the point load only. So we can get the optimum equation by simplifying, that is half of E into integration of x is equal to 0 to 2L E square A into dx minus ui into p for 1D elements. Now we know that E minus E and u relation, that is E is equal to del u by del x. So half of epsilon, that is strain, is equal to del u by del x. So half of E into A is having the integration of del u by del x bracket square into dx plus A2 into L square. Why we have taken u equation that we have already found, u is equal to A2 into x in bracket x minus 2L. So even at L is equal to, if we have put, you will get the value of u1. So we have taken up this value of u1 at length L. So it is A2 minus A2 into L square, and we have put that in equation. So we know that del u by del x will become del by del x, and putting a value of u, that is A2 into x in bracket x minus 2L, and it will become as optimized equation, that is 2A2 into x minus L, and if we put this value in the potential energy equation, so it will become half of E into A, 0 to 2L, 2A2 into x minus L bracket square into square 1 dx plus A2L square p, and if we optimize this one, and if we take the integration of this, so by putting the values and the limits over here, we can get the final solution over here, that is pi is equal to 4 by 3 E A into A2 square L cube plus A2 L square P. This is the equation number 2, and now the time is for putting the condition of minimum potential energy. So, we have to put del pi by del A2 is equal to 0, and we can take the derivation of this equation, partial derivation. So, we have the value in equation number 2, and we will put the values over here, and we can get the value of A2 is equal to minus 3 P upon 8 EAL, and deformation is equation 1 becomes u is equal to A2 into x minus 2L. So, u will become, and we can put this value of u over here, a value of A2 in equation u. So, it will become the minus 3p 8EAL into x minus 2L, and we can put it as equation number 3, and for this we can have epsilon is equal to del u by del x and minus 3p 4EAL into x minus 2L, and also we have the relation stress is equal to E into epsilon. Thank you friends, thank you very much. Lastly, we can see the behavior of this potential energy. So, we can conclude that the deformation is 0 at x is equal to 0 and x is equal to 2L, that is at extremized conditions, that is x is equal to 0 and x is equal to 2L, the deformation is minimum, and it will be maximum at the mid, that is where load is acting, and load is acting at x is equal to L. So, we can have this one. Thank you very much for the beautiful support.